Thank you very much for the organizers here to organize such a wonderful event, and I enjoyed every talk of yesterday. I really appreciate this opportunity to learn a lot. And this is really choosing this topic really in honor of René. And I first time met René was 1998 fall. I still remember it because Larry at that time was my advisor, and he told me that I'm going to take you to Princeton, and there's a very smart people there, René. I was like, okay, it's not very easy to hear such a comment from Larry. So I went there, and I was still a last year of my PhD. That was 27 years ago. So I met René, and René was talking to me with this energy and intensity and enthusiasm. And I was a PhD student. I found no state space, no time space to even talk back, because we're just talking so enthusiastically. And this energy was really very inspiring to me as a junior researcher at that time. And I found it incredible to see him still have the same level of energy after 27 years. You know, René, the one thing that we used to share in common was the commute. René used to commute from West Coast to East Coast for how many years? 30 plus years? 40. And I used to have that two-body problem. I remember Erhan was telling me, he said, oh, now you're in a race with René. And I stopped after 7 years. It's unbearable. But it's incredible to see the energy level of René throughout of so many years and with all these students here. And I was really thinking, when I was preparing my talk yesterday, generation like me and a generation younger, we were really fortunate to be among this technical giant of this group of probabilists, starting from Nico, Terry, and Larry Lyons, Terry Lyons, and Terry Lyons and Lyons, and all the people. And of course, René is one of these representatives of these people that give us this passion, this dedication, and this vision for the field and the leadership. So we were really very fortunate to grow reading their papers and reading their books to be part of this community. And so I really, this is very inspiring to, even though we never worked together, but for me, this is the role model to push us to this next level. So it's incredible for us to witness all this giant here. And it's a very humbling experience as well to be here talking about some of the work that was inspired by all these people. Yeah, okay. So I will talk about this continuous time mean field games. And this is a joint work with my former student, Anran, now is at Columbia, and my former postdoc now is in Chinese U of Hong Kong, and my collaborator, Yu Fei from Imperial College. And of course, mean field games, everyone knows about it. And I'm just going to say a few words that will set the tone of, or the page of what I'm going through. So of course, this one of the things that mean field game was invented or created was trying to find an analytical, feasible way to characterize the otherwise difficult Nash equilibriums or general n-player games. And in this Nash equilibriums, in mean field games, it has two components. Of course, the usual optimality condition, as you will see in any of the games, where when you have the homogeneity of all the players, these representative players, the strategy is optimal given a population distribution. That's really where the mean field game is coming in. And of course, because of these homogeneity conditions, you also need to ensure that there's a consistency so that the induced state dynamics by the optimal control is going to match the population state. Okay, so that's a very natural stuff. And because of this, of course, there are many variants of this, but the three main approaches of characterizing Nash equilibriums are, one is AGB Fokker-Planck, where you have the forward and backward iterations so that you rely on some functional fixed point method to find the Nash. And naturally, from this forward-backward approach, you have this probabilistic approach, which is the BSDE. Then, of course, then you can also consider, in general, without this forward-backward, you consider the coupled AGB forward of Fokker-Planck, and you consider the space of probability measures, and then you consider this PDEs. So this is the mass equation, and we have all these major players here doing this. And of course, in order to analyze the Nash equilibrium, you have to have some assumptions. And one of the typical assumptions is this convexity of the Hamiltonian. Or if you don't assume a priori, you want to have the uniqueness of this minimizer or optimizer for the Hamiltonian, which in general, if you look at the corresponding control problem, that induces the optimal uniqueness of the optimal control. And the other one, of course, if you don't assume the uniqueness, the convexity of Hamiltonian usually put a lot of constraints on this underlying this game structure, including the action set has to be convex, or you have the linearity of the drift, and also the running cost functions to be convex. So these are the typical assumptions, and a lot of analysis and applications has been developed. In the meantime, where this other piece of primal-dual comes from is really coming from this linear program approximations or formulations for stochastic control. Okay? So this linear program, in many ways, is not as popular in the general math community, probably because when we think about linear program, we think about discrete states, discrete action, and that seems to be more in what we call OR field. And however, the linear program formulation for stochastic control was really envisioned as early as in the 1960s, according to many of the stories by Dinkin. And this, in many of the formal literatures you can find, is really starting from these, as you can imagine, as Dinkin used to claim that stochastic control problems is just an infinite dimensional linear program. Okay? And of course, then if you look at the discrete time models, the Markov decision processes with finite state actions was really established formally in the 60s. And then later on, there's variants of approximate dynamic programming developed in its OR field. And then continuous time models was really the prominent one was in this group of Kurtz and Stockbridge, where they really connect this stochastic control problem through, with the linear program through this controlled martingale problem, which we will also use here. And in this mean field community, Peter, see here, yeah? So they, with the mean field control and the stopping, Peter and a group of these papers here, they started looking at the think about these 2 layers or 2 steps of mean field games. The first step is you fix the population flow. It's just a stochastic control problem, and therefore it's very natural now to translate this control problem through this linear program. And of course, the tool here, or the key tool here, or key concept here that connect the control and linear program is what is called occupation measure, okay? And I'm going to go through that later. But in general, linear program itself, many people are familiar with linear program. When people study linear program, it's not just a linear program. There's usually a twins of the linear program, which is the dual problem. So you have the linear program is considered a primal problem, and the dual problem is the one that studies the control, the counterpart of the control. Okay, and so why this push from the linear program to the control to the dual problem was not that well studied. One of the reasons being, when you think about the dual problem, is really trying to characterize the multiplicity of this optimal control. And in general, that's not a focus. And if you assume existence or a uniqueness of control, and then where the task is accomplished. But in general, in this a couple of years ago, we had this a little bit of progress here about considering discrete time mean field games. And if you use this primal-dual formulation, not just looking at the first layer of the stochastic control translation of linear program, but you actually push to the other side, also looking at the dual formulation of the problems, then you could use this primal-dual formulation, at least in this discrete time setting, to characterize all Nash in the mean field games. Okay? So in general, think about all Nash. In general, in games, when we think about Nash equilibrium, you give me a strategy, and I could try to decide whether this is Nash, or we have this analytical method of fixed point method, and then in learnings, we have various algorithms to find Nash. But characterizing all Nash sets was not in the effort for many years. And in this primal-dual formulation, we were able to translate this set of all Nash as a feasible solution or feasible set of another optimization problem. So what is the benefit of this? The benefit of this is, first of all, when we do learning or when we do study, and as yesterday, several talks, we actually see that there's this need of analyzing the robustness of Nash equilibrium. When you have a model disturbance or when you have learning uncertainty, you want to know how the analysis is responding to these errors in the Nash. Secondly, when you have these characterizations of Nash set, then what you can do, for example, when you do Stackelberg game or when you do any other principal agent problems, you have 2 layers of problems. For example, you have a central controller that optimizes something, and then you have a large population on the different layers where you need to characterize the Nash. And in this case, if you can characterize the Nash equilibrium, and then you translate that Nash set as a constraint, if you could do that, then you basically translate this multiple layers of optimization problem into a constraint optimization problem. Okay, so that's another important part. And on top of that, when you translate the Nash set into a feasibility set of an optimal optimization problem, what happens is, as long as your optimization problem is not too ugly, meaning that if your constraint set, you can fold it into your objective function, as long as your constraint is convex. If your objective function is not convex, it's okay that there's certain algorithm you can still do randomization for initial points that allows you to characterize or find the Nash. Okay, so that's another thing. So because of this characterization of Nash through the primal-dual, then it's really opened the door to a lot of optimization algorithms, in fact, not just the PDE method, that allows us to say, policy gradient, and in fact, we did provide this performance guarantee to show that you can guarantee to find all the Nash if you give a good initial positions for the optimization problem. So this is basically the summaries of these things that we are trying to understand. What is the primal-dual for mean-field game, where it's coming from. And of course, this is all in the discrete time. And for us to really come to this step now is to think about discrete time sounds a little bit far away from many of our interests, because we like PDEs, we like all these things. Those feels a little bit OR, okay? So the question is, can we also develop continuous time primal-dual formulations, okay? And also, given all this last almost 20 years of development of these mean-field games, is there still a benefit of developing a primal-dual formulations, and is any really advantage other than just optimization algorithmic advantage? And also, to understand that, we need to actually compare with existing approaches to see in what difference this one is going to give you. And when we had this discrete time mean-field primal-dual, it's very hard to make a comparison because we usually have all these approaches in the continuous time. So let's try, push to see what we can do with the continuous time. And through this lens of continuous time, let's see what this difference is going to tell us. And that's exactly what we're going to do. So we're going to establish this primal-dual formulation. I'm going to explain in details. And then on top of that, we want to develop these formulations so that we don't have to be restricted by the Hamiltonian's convexity or the uniqueness of the Hamiltonian. Okay? And then with this non-restriction of this on this Hamiltonian, then the comparison to this, I'm going to take just one example rather than all the three different approaches, just compare with AJB Fokker-Planck equation. Okay, sorry, typo. With some examples. Okay, so this is our setup. So what we're going to do is let's fix a finite time horizon, and the analysis should be going through. We're still working on it for the infinite time horizon. And then I'm going to, in this case, look at the state space that is in RD and a complete separable metric space for these actions. And what is going to be different here is I allow, if you have a diffusions, I allow this drift and diffusions all depends on time, state, and action, and the mean field, okay? And all the running costs are also going to be on this. And then the initial distribution of each player is going to be represented by this row that I'm going to come back. So the first step, of course, is primal. Primal is what we call the linear program formulation. And this is not difficult to really envision. So suppose I start with mean field, and I fix the mean field flow. Then now I can focus on my stochastic control problems. And in this particular setting, I'm going to look at the feedback type. There's a feedback control that is the mapping, and it's a relaxed type. It's very important here we do a relaxed type, and it's going to measure, map this time and the state to this distribution of actions. And when I look at relaxed type, then I'm going to change accordingly the drift and the diffusion term according to this relaxed policy. And then I will have the usual relaxed control problems that I have the diffusion, and then I have the objective function that depends on the terminal cost and the running cost. Okay, so this is control problems. And this has been done to formulate a linear program. This is really borrow and continuing the wisdom of many people earlier, including Daniel has also used this connections of this control diffusions and the weak formulation of the martingale problems. So in order to formulate from a stochastic control problem to this linear program, there are two variables that we need to look at. One is we need to think about the distribution of the state at terminal t. And then also I need, for the linear program formulations of controls, one of the key components, as I said, is the occupation measure. It's the occupation measure for any stochastic control problems, and this occupation measure really measures the state action distributions over a finite time horizon. So this is where I need to do. So if you think about, look at these corresponding martingale problems here, the only thing I need to specify is this nu, the distribution of this at the terminal time t, and also this c, which is the occupation measure. And the rest are naturally coming from this infinitesimal generator of the associate control diffusions. Okay? So how do I actually construct this? So the two variables are nu and c. If I actually rewrite this objective functions linear program, then I can rewrite it into this, in terms of the occupation measure and in terms of the terminal values. And then how do we make sure that when I have the linear program with this representative, these two variables, nu and c, and then it's actually connected to this control problem through this martingale formulation, then I need to, I already specified, rewrite the objective function in this way, and then I just have to carefully define the admissible policies, TPO. So the equivalence is very easy. We show that if you assume that the A is polished space, and then also you have enough boundedness and measurability on these cost functions. By the way, this is different from the earlier work of this linear program, where usually you assume more continuity on these things. But in our case, for us to be able to formulate the dual problem for the primals, we do need, because the controls are going to be only measurable with respect to the state, we do need to relax it to be able to deal with these boundedness and measurable functions of B and sigma. And the first important thing is to show that the control problems that we have with this closed loop, by the way, we're going to fix on closed loop, but the open loop is actually equivalently can be satisfied. We consider the closed loop policies and show that for a control that with a mixed fixed mean field flow, the control problem is equivalent to, on the right-hand side, the formulation of the linear program with this fixed set of admissible policy, admissible set of nu and c. And the way to do this, of course, to write the particular form of this linear program is not difficult, but the difficulty is actually to map the mu c and the state and the policy. Okay, so that's the key part of defining this. And so from one direction, when I have control diffusion through this linear program, through the occupation measure, that's very easy. I give you a admissible control a state policy pair. So give you a state, give you the control. And then this induce this occupation measure is just by direct definition, is that you want the terminal distribution is going to just calculate the distribution at the end of t. And when you actually define the occupation measure, you just calculate the time that the state and the action pair stayed in the particular region of the probability space, okay? So that's very easy. That's from x gamma to nu c, that's easy. The other direction is more tricky. Oh, this one. I give you a linear program, and I have an associated occupation measure. How do you ensure that you can define a control diffusion? Meaning that you have to be able to construct a corresponding state x, and also you can also construct the gamma, which is the control policy. Okay. Well, it goes through 3 steps. The first one is, of course, the important thing is to show that the idea is to show that for any occupation measure for the linear program problems that really characterize the linear program is going to induce this state and control pair. And the first one is you do this integration. Okay, I give you the occupation measure that depends on t, state, and action. Then you just do this conditional sequence of conditional law. So you just do that first. I look at the marginals of this occupation measure on the time and the state that give me the policy. And then I do another layer. Given these controlled, these marginals you can see on the T and RD, I do another layers of peeling, and then I get the mx, which is really you can imagine this as a curve for the probability measure by which you need to show, well, that I can peel this mx and show that this is what we call the mimicking. You want to have a flow of probability measure such that this mx measures this controlled diffusion at the terminal t and at the initial time 0. Okay, you can do that. And then you need to luckily we found this work 2016 saying that if I define this mx in this way and it's continuous, then there exists a process x such that this process is exactly the weak is the solution of the weak formulation of the controlled process characterized by these infinitesimal generators of the control process. Okay, so then the story is complete. Okay, so this is the first layers where the linear program and the controlled diffusions are said to be equivalent. And this is very similar to what earlier works has been done, Peter, and with a different setup, but a very similar recipe. The next one is the critical one, is you don't just stop at the first layer of the stochastic control, because in order to study the Nash equilibrium in mean field, you do need to go to this consistency. You need to actually study this Fokker-Planck, and then how you actually make this AGB and Fokker-Planck talk to each other. Okay, and in this case, you need these dual formulations. And what is a dual formulation? Once you have a linear program, you have the linear operators, then there's tons of functional analysis, abstract space that allows you to write down the dual formulation of the linear program. And in this particular case, if you take the abstract formulation of the dual space of the linear program and specialize to this controlled diffusion, then you can see that, in fact, the dual problems now is just the supremum taking the maximization over all smooth subsolution of AJBs. Okay? So now you see that now this dual problem is another linear program, and with its objective function specified by the initial row of the control diffusion, the starting point, and then this subset is, as you see, is the collection of the subsolutions of the AJB. Okay? So now if you think about this, if I have this, then I could, first before I say that, you can easily see that I have the linear program and I have a dual, and now in the linear program and dual problem, in this general linear program formulation, you naturally have this weak duality, which basically says that the upper bound of your dual problem is going to be the lower bound of your linear program. Okay? The question is, how do you actually, in linear program formulation, one of the key things is when you start from linear program to the dual, you need to ensure that, well, there are many of the different linear programs that can give you the same value, but you need to ensure that the set is just right side, that when you actually look at the dual problem, there's no duality gap. Okay? Meaning the dual problem and the linear program give you the same value when they actually achieve the optimal value. So in that case, I put this primal-dual together. Okay? Now you look at this, it's just like a laundry list. The primal feasibility is just, as I said, this is a controlled martingale problems for this associated stochastic control problem. That's a primal. And the dual problem is just nothing but the collections of these subsolutions of the associated AJB. And the primal dual is that you want to make sure these two solutions are the same. You put them together, you get this equation for the primal dual. And the last one is a consistency to show that, to ensure that the optimal mean field flow is going to be also the corresponding to this occupation measure of the linear program, which induce the underlying controlled diffusion. So this is the primal-dual formulation. And then if you look at this, you say, so what? We still have this like AJB, and we have this linear program. What do we gain by looking at this system? Okay? So now, let me show you what we gain. If you combine this equation, if you combine this equation, combine this, the first equation with the second, you get this. Is you look at this equation, this is your dual variables, which is going to be the solution or maximizer of all these subsolutions of the AJB. And then you have this one, which means that the dual variable, the optimal control, is going to be only matching the terminal condition only at the support of the optimal mean field flow. Okay? And if you look at the second one, it also shows that this solution of this dual problem is only going to satisfy as a solution of AJB. I don't know why my computer says AJB. Only the support of mean field flow. So this is really for all of us who are very familiar with stochastic control, is a reminiscent of this stochastic control problem when you look at a joint equation that tells you that the optimal solution, optimal control, is only needed on this joint equation, only on the optimal flow. Okay? And in the mean field, this shows that when you try to solve this dual variable, you don't need to look at the entire AJB equation, and instead, you just have to look at the solution at the support of the optimal mean flow. Okay? So this is the analytical insight when you actually look at this. And I really wanted to make a remark here that this system is consistent with what Pierre has done many years ago that we only found after we finished the paper, where a special class of mean field games was also studied where there was no diffusion control, and when Nash uniqueness was assumed, that you could also find these representations of these primal-dual systems. Okay, so I have 5 minutes, and I want to see the first remark is the primal-dual tells us that when we were trying to find the Nash equilibrium, when we tried to use AJB, Fokker-Planck, or the master equation, we were doing too hard to try to find the Nash. We do find Nash when we actually have the convexity of this Hamiltonian. We found that one. But in general, in order for you to find all Nash, you can relax it so that the AJB can relax so that it give you a lot more choices of the dual solutions. And of course, the important thing is to ensure that this strong duality holds. And I just wanted to comment that the strong duality system here, it characterizes all the Nash. And in order for us to derive the strong duality, what is interesting is that it becomes characterizing the regularities of the associated AJBs. And in the cases when you have the control diffusion, then you really, AJB is fully nonlinear, then the one that we could utilize. And of course, there are many regularities, studies of fully nonlinear PDEs that could give us this insight of when these assumptions are needed to ensure this strong duality. And in the case of the controls is not on the diffusion terms, then the AJB becomes much simpler, it's semi-linear, and then these studies of all these controls, regularities become much simpler. Now, I do want to show, in addition to that relaxations from the primal duals, I want to show some examples. Of course, the first message is the primal dual is consistent with the current AJB Fokker-Planck dual equation when you actually have the equilibrium flow has a full support, and when you actually have the uniqueness of the Hamiltonian. What is beyond this is that I'm going to show you one example is when the equilibrium flow doesn't have full support, then you can find a lot more Nash equilibrium than the AJB approach is going to give you. So this is just to show that this is equivalent to this AJB. And then this is a simple example. When the Hamiltonian has multiple optimizers, then let's take a very degenerate mean field games where the running cost and terminal costs are all 0. Then you actually can use a primal dual to find all the Nash equilibrium that corresponds to the dual variables to be 0. And in this case, of course, you can't really easily use the AJB Fokker-Planck equation to do it because the Hamiltonian is not unique. The interesting thing here is this one, the last example, is that if I have a mean field game, let's take a very simple, just a two-state action space, and I have the drift is just a constant and sigma. We don't have controls on the sigma, and sigma, there's no noise. And then if I start with a very simple distribution from a particular point, and I choose this particular functions, cost functions, in this case, you can have the optimal mean flow is actually just at x0 and follow to t. And you have, in this case, the AJB equations has only unique viscosity solutions and is not differentiable at 0. But then you could have many Nash equilibrium through this primal-dual formulation. And these are just the constructions. You can take just rewrite the primal-dual formulations, and you could write down infinitely many of the dual variables, which are all Nash. Okay? And the key point here, as I said, is really the dual solutions only has to coincide on the support of the optimal mean flow. Okay? So of course, this is what I want to say. Currently, we have several questions that we are still trying to do, which is, of course, now you have the primal-dual, so what? And one of the things is try to find, other than these trivial examples, some examples where even for us to understand what this Nash is really characterized by this dual, and we are looking at a linear quadratic cases where the Nash, we know Nash, but we don't know all the Nash, and that's the work we're doing. And of course, mean field gain without adding a common noise is not a complete story, so we're working on this. And the key technical part when the mean field with common noise is this still this linear program formulation. When you add the common noise, there are many different ways of formulating the linear program. The problem is what is the right size of this of the constraints so that the dual variables is going to be exactly matching. So that's the tricky part. And the other thing is now we have this characterization. It's become much easier for us to study the convergence of n pairs of Nash, because now characterizing the Nash equilibrium n pairs, we can do that, okay? And then go into this convergence to the primal-dual systems, it just becomes very analytical, okay? You really have analytical tools to study the convergence of the Nash from the n player to this mean field. And of course, this is many things that, and the numericals. So in the discrete time, we have the numerics that we can borrow a lot of tools from optimization. Now in the continuous time, you have the primal-dual. What are the numerics that we can design so that for the first time, we can try to take a look at all the Nash that we don't know. Okay, so this is what I'm going to talk about, and thank you very much for your attention.